Okay, so the sad news is this. One of my favorite units to teach, which is this unit on differential equations, is also the shortest unit in the course. I wish we would spend more time here. I think you've all heard me say this before. Like when you go to college, if you're studying engineering, medicine, business, science of any sort, you're going to take a whole semester-long course on differential equations. What we've done is going to get you like 1 or 2 days. 1 or 2 days into the course, maybe not even that far. Okay? What we know with differential equations is that it is an equation that involves derivatives. Now there are the simple kind, where it just says like dy dx equals stuff in terms of x. Everything on one side, it's all x values. Okay. Then you've got what's called separable, and that's when things look like f of y times dy equals g of x times dx. In this first case, because everything is on the right-hand side, everything is a function of x, we know that in order to solve this, we just integrate and we're done. Right, you're done. Over here at separable differential equations, you guys quizzed on this last week, you're going to separate the variables if you can. You're going to integrate both sides if you can. And then you solve for y, use the initial condition, get the constant of integration. We're okay with the process, right? Now, what's your goal? Regardless of how you're doing this, your goal is what? What are you trying to get to, other than the right answer and all the points? What was that, Andy? You're going to look for domain restrictions for sure, but what's our goal? What are we hoping to get at the end here? Not an equation. I'm looking for something more specific than that.
Looking for what?
A function. You want a function, and not just a function. It has to be a continuous function, and you need a continuous function, and you need, and Andy, this is what you said earlier, you need to indicate the domain. Okay, now that is what's considered a perfectly solved differential equation. Whether it's the simple kind or the separable kind, you want to get to a continuous function with the appropriate domain. The reality is, there is this whole other world. These other I'll just call them other diffie Qs. The reason that we study these in Calc AB, these are the easy ones. These are the easy ones. This is maybe like the hand-selected, probably less than 5% of the whole world of differential equations. There are some exotic techniques out there named after many famous mathematicians like Laplace and Fourier and Wronskian. I can never remember his name. There are so many powerful things that are in your future, sadly not in Calculus AB. In Calc BC, you look at logistic differential equations, you look at Euler's method. There's all these things. The last thing for us is a technique that works all of the time, and it's called, let me just write it over here, it's called a slope field. S-L-O-P-E-F-I-E-L-D. Slope fields are not going to give you the solution. Slope fields are going to tell you what the solution looks like. I want to say that again. With a slope field, you're not going to get a continuous function and its appropriate domain. You're not going to get an equation. What you're going to get is an idea of what the graph looks like. That's your goal with the slope field. And so over the course of the next 40 minutes, we're going to look at that. We're going to play around with it. You're going to get to color a little bit. You're going to want to get some markers out of the supply kit. You're going to need them. You're going to need your calculators. All is going to be well. I need you guys to just take 2 or 3 minutes to read through the introduction on your own. Be ready to ask me any questions that you have. I'm over here on page 17. I'm going to need 2 students here to take attendance.
I don't know about you.
I'm not able to help you out right now. They are reading. I'm taking attendance. Your grandparents will be here in less than an hour. Jackie reading. You're doing Jackie reading. Let's little tap on your nose when you're done reading, so I know we can move on. We can tap on your nose, not on somebody else's nose. That's weird. We're close, but not that close. Okay. Take another minute. All right, friends. So what questions are out there on the reading that you just did? We only had a couple minutes. Yvette, what's your question?
Why can't you solve the dy over dx equals x minus y?
Ah, such a good question to get us started here. dy dx equals x minus y minus 1. Would everybody agree that this is a differential equation?
Yes.
Right, we've got an equation, we see the derivative. Now, does it count as a simple differential equation? Is everything on one side in terms of x?
No.
No.
No, so we can't just integrate. Is it separable?
Yes.
Yes.
Well, no, here's the thing. Some of you guys are answering yes way too soon. It's only considered separable if you can legally, using algebra, separate the variables. And so what are some of the ideas that we might try? Take anything from anyone. Jose, what could you try?
Well, first multiply the dx.
Okay, all right, that tends to be a good opening move for us, and dy is x minus y minus 1 times dx. Okay, we have not separated the variables yet. What else could we try to separate the variables here? Yeah?
I thought before multiplying by dx you could add y on both sides.
Okay, so you're seeing a different approach. You're like, let me add y to both sides. Okay, so then dy dx plus y equals x minus 1. Is this legal?
Yeah.
Legal to add y to both sides. Legal to multiply by dx on both sides?
Yeah.
Sure. Have we separated the variables in either case?
No.
No. So what else, Henry?
Like the next move would be to multiply by dx, but you're gonna end up having dy plus dx times y.
If you multiply both sides by dx here is your next move. Well, dx times dy over dx is, God bless, is dy. Dx times y is y dx equals on this side x minus 1 dx. The right-hand side looks good, the left-hand side doesn't look good. You've got the y and the dx mixing together. And you could try some other things. You might say, well, what if I subtract something? It won't work. There is no technique available for separating these variables, which means we can't do the simple technique. We can't separate the variables. In our world right now, we are stuck, which is why we're going to go to a slope field. So, Exhibit A, here's your slope field. This slope field is there to give you an idea of what the solution curve looks like. Yes, Jackie, you are going to be expected to make a slope field.
Wow.
Sometimes by hand, sometimes with the assistance of some technology. I want to explain what a slope field is, and then we'll go from there. The slope field represents little tangent lines to your solution curve. What we know is that this slope field is for the differential equation dy dx equals x minus y minus 1. And although I don't know what the solution curve, oh, Jesus, camera over here. I don't know what the solution is. What does dy dx tell me? What does dy dx tell me? It's the derivative. What is it really? Derivative is short for something. Slope, be specific.
Slope of.
Slope of the what? Slope of the tangent line. The way a slope field works is you pick a point, like for example over here at the origin, 0, 0. Andy, hi, need to wake up. at the origin 0, 0. You pick a point and you plug that point into your differential equation. So at the origin 0, 0, what's the slope?
Negative
X
1.
minus 1.
It's
Wait, no.
x minus y. 0 minus 0 minus 1. What's the slope?
Negative 1.
Negative 1. So this little tangent line here has a slope of negative 1. That's just for that one little point. Now there's an infinite number of other points to consider. So you might go to the next point. Like you might look over here at 1, 0. At 1, 0, what's the slope going to have to be? If I'm over here at 1, 0, 1 minus 0 minus 1 is 0. Look at your slope field. What did we draw there? A little horizontal tangent line. This has slope of 0. Now you might start to panic a little bit because you're going to see all these other little tangent lines. And you might start thinking, oh my God, what's the homework going to look like? I don't have time in my busy 18-year-old life to go and make all these little tangent lines. We're okay? But you can, as much as you want to, given a differential equation, make a slope field. Here's why you make the slope field. The tangent lines tell you how the curve behaves. So let's jump into this with part A. Using the slope field shown above, I want to sketch the solution. So the sketch the solution just means, what does the solution look like? You're not going to come up with an equation, you're going to come up with a sketch. What does the solution look like? What you're going to be given is the differential equation, we already have that. And you're given this initial condition that y of negative 2 equals 2. So if x equals negative 2, the y value is 2. Find that point in your slope field. We'll do this first with a pencil, then when you think you get it, we're going to move on to the pen. So find the point negative 2, 2 in your slope field. What's the tangent line doing at negative 2, 2? The tangent line is decreasing. If the tangent line is decreasing, what's your curve doing? Your tangent line is touching the curve at this one point, right? So if your tangent line is decreasing, what's your curve doing? Also decreasing. And you might say, okay, that's fine. That's what my curve is doing. What you're going to do is you're going to follow the curve, and that curve takes you to another tangent line. What's that tangent line doing? Decreasing. You continue to decrease. So the black represents my solution curve. I get to another one. Well, I'm still decreasing, but maybe not as much anymore. Well, actually, I do that badly. We're decreasing, and I see more decreasing, more decreasing, more decreasing. You're just sort of following along on the curve here. We're decreasing, 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 decreasing. Eventually, you start to see where the tangent lines flatten out. If we're following along, so what are you going to do with your curve? You're going to flatten out. After that, your tangent lines start to increase, so you increase, 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 increase. You can follow your tangent lines to the right, and you want to follow your tangent lines to the left where they get more vertical. What I just drew in black is the solution curve. This says this is what my solution to this differential equation is going to look like if I use this as my initial condition. So a couple of questions. Does our solution meet the criteria that we're looking for? Yes. Is it a function?
Yes.
Does it pass the vertical line test? Is it continuous?
Yeah.
Do we have a domain?
No. All real numbers?
We didn't really indicate what the domain is here. What is the domain?
All real numbers.
Wouldn't it be all real numbers? This guy continues going to the right, this guy continues going to the left?
Yeah.
Now here's the thing. You might be like, but wait, where's the equation? Where's the like y equals stuff? That's not your goal. Your goal with the slope field is to say, oh, this is what the solution looks like. Okay? So with that said, that's part A. Check. I'm doing that one in black. I would recommend that you like take out the different colors. Trace with the pencil first, then go with the marker.
This pink is mad. Too bad.
Alberto, you doing that? Change it.
Which full metal?
So you're sketching the solution to the same differential equation using the initial condition y equals 2 and x equals 0. So go find that point. Then follow your tangent lines. I just need a sketch. We're not going to go to all OCD. So I'm going to use red for this one. I'm not going to use red because that's a bad one. X equals 0, y equals 2. I'm going to go find that point on the curve. I see a tangent line. My tangent line is decreasing. And I follow that tangent line. And that tangent line gets me to another tangent line, to another tangent line. And I see those tangent lines, they start to flatten out, and then they start to increase. They should look something like this. As you go to the left, they increase, 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 increase. That's my solution for B. That's going to be in red. Paul.
What if like you went further down, but like
What if you mean if you went further down?
it looks like that, but it's not.
Oh, you mean like if your curve went down a little bit further than mine? That's fine. I don't want you to get all OCD. We're trying to figure out what does the curve look like. It's not going to be super precise. Henry.
The outgoing one at the very beginning, we plugged in 0, 0. But
We plugged in 0, 0 just so I could show you like where the little tangent line was coming from. We were getting the slope from the differential equation. We need the slopes to determine how the curve behaves. Now let's look at this last one. The last one I'll do in green. 5, 2. X is 5, y is 2. Find that point on your solution curve. Then give me a little sketch. There's something very specific I'm looking for in your sketch this time.
Is it a straight line?
Maybe there's a domain restriction. I don't know these things. Find that point 5, 2. 1, 2, 3, 4, 5, 2. We seem to be over here somewhere. Follow the tangent lines. This tangent line's increasing, which means my curve was increasing at that point. What about just before it? Right, I can follow these tangent lines to the left as well as to the right. What you should see is something that looks like that as you connect those tangent lines. Yvel.
Wait, what direction do you follow the lines? Like,
Both directions, to the left and to the right.
or like when, because I just got a straight line going like to the left. Well, not to the left. But you always went down instead of being straight.
Well, so you're at 5, 2, and so are you thinking that you're on like these guys here
Yeah.
that are all pointing in the same direction? I can understand how you might get that. We're gonna look at this. We're just sketching. We're just sketching by hand to get an idea of what's going on. Is everyone mostly okay? This should be the easy part. It's almost like a connect the dots. Okay, now let's push the thinking a little bit more. Because you are going to be asked from time to time to make a slope field. And I want to make sure you know how to do this on the computer. So if we don't mind, Paul and Roberto, I need you guys to switch seats. I just said on the computer, I meant on the calculator. Okay, so you guys are taking out your calculators. Let me get Paul set up over here. Paul, there you go. You're good to go. Sorry. And Harper.
Is it a good enemy? I can't trust you. Suggestions.
All right. All right. We're good. Paul, if you could maximize that so it fills up the whole screen. And Kevin, if you could turn off the lights in the back, please. Or I guess the lights for the front part. And then Paul down here, can you click it up to 200% or as far as it'll go? Okay. Everybody's got their calculator?
Yes.
All right, so I want to show you how to sketch these slope fields or create slope fields on your calculator. This is a really good skill for you to have. So you're going to go to Menu. You're going to go to, whoa, Paul, where are you? Paul, escape. Go back to the home screen and go to Graph. Graph, there you go. Menu. And Graph Entry Edit. I want you to look at this with fresh eyes for a second. You have probably never actually looked at this screen before in this way. You have a lot of options on this menu here. You can graph functions, you can graph equations, you can graph parametric curves, which was something that would have been done last year in pre-calculus, maybe. Destiny's giving me the look, so maybe not. Anything else?
Differential.
Diff-EQ, which stands for differential equations. Go down to differential equation. Your screen automatically changes. Automatically changes. Check it out. You've got y1, and then this little prime up here. What does that mean? It means the derivative. What is the derivative equal to? What I want you to graph is I want you to graph dy dx equals x minus y minus 1. So just enter it in, x minus y minus 1. Now, if you hit enter right now, and feel free to hit enter right now, nothing happens. Absolutely nothing happens. Paul, hit that again, and arrow up to y1. The issue is this. The name of the function, the name that you typed in is y1. So you need to type in x minus y1. Andy, I need your numeric card. So x minus y1 minus 1. Y1 here because y1 here. We want them to match. Hit enter. Look familiar? This is the slope field that we were just looking at. Now, it's not as precise. It doesn't have as many little tangent lines as the other one did. You could change that if you wanted to. But this is how you make a slope field. I want to show you how to make the solution curves. Okay, so what was that first initial condition, the one that I did in black?
-2, 2.
Negative 2, 2 is the first one. Okay, Paul, hit menu. Oh, I'm sorry, just hit tab, my bad. Hit escape, and then tab, arrow up. This guy over here allows you to put in your initial condition. So type in negative 2, 2. So negative 2, comma 2. And then hit enter. That's the solution curve. Does that match what we sketched by hand?
Yes.
Maybe not perfectly, it doesn't have to be perfect, but we've got a sense of this, right? What was the next one that we did?
X equals 0, y 2.
X equals 0, y equals 2. Let's do that one. Hit tab. Arrow up. Now, you can, if you go over here, click on the little plus button, it gives you a table so that you can put in more initial conditions. So put in that next one, 0, comma 2, hit enter, and if you hit escape, that'll go away. Now we've got that second one that we sketched, and it's behaving the way that it should. That last one that I asked you guys to sketch, I think was the point, was it 5, comma 2? So go on over there, add another initial condition, 5, comma 2, hit OK. And there are all three solution curves on your graphing calculator, and they match closely enough what you had by hand. All the friends are okay?
Yeah.
Kaylin, you doing all right back there? Paul?
How does it go from like a line to this?
So it's because of the technique that's being used here. What the calculator is doing is it says, okay, let me plot a point, let me find the slope, let me move. Then I get to a new point. It's not actually connecting the dots like it would if you were sketching a curve, and it's just the way that the program is set up. But that's a good question. It's just a bunch of dots. Really, it should be a curve. The calculator's not connecting the dots. All the friends are good? So this is the slope field. Paul, your job here is done. I want to give you guys a little bit of time to see what you can do with model problem number 2 on the bottom of page 18. Paul, you did a great job. Roberto, you can go back. And Kevin, if you can turn the lights on in the back. See what you can do with this one. We'll talk in a little bit. Sylvia, are you finished? Rebecca, you should be out of time pretty soon, right? Okay. Start at the right is the slope field for the differential equation dy dx equals square root of y over 2 minus x. I'll be there in a second. Starting at the point 3, 4, use the slope field to sketch the particular solution. Now, starting at the point 1, 4, use the slope field to sketch the particular solution. Some of you all have some good looking curves. Starting at the point 3, 4, use the slope field. So I find the point 1, 2, 3. I'm going to go up 4. I see a tangent line there. That tangent line is telling me that I'm supposed to decrease. So I decrease. I get to another one that says keep decreasing, but it seems to decrease a little bit less, a little bit less, a little bit less. And we see these guys are flattening out. Is everybody mostly okay with this first one? Okay, things are matching. Okay, now I go to the point 1, 4. 1, 4, here I am. Then I go up to 4. I'm over here. I'm going to increase to the right. I'm going to decrease if I'm reading this to the left, and I'm flattening out. This is what my solution curves are looking like. Now, use your newfound calculator skills. Make sure that we're not lying to ourselves here. Is the slope field right? Is your solution curve right? You got good curves. You got good curves too. Diego's not really curving a lot. Must be the hood getting in the way of your seeing things right. All right, so a couple of things I want to point out about this slope field. Anybody notice anything different about this slope field than the last one? Take a look at both of them side by side. Flip back and forth a little bit. Marilyn sees something different. Henry sees something different. Sheila sees something different. Destiny sees something different. Sheila, what do you see that's different?
So slope field isn't like covering both the the first and second
The slope field isn't covering the whole graph. Ever see that? You've got tangent lines up here, but you don't have tangent lines down here. That is definitely something different. Anybody have a suspicion as to why? Why are there no tangent lines down here, Marilyn? What's your suspicion? Because of domain restriction? I disagree with you on domain restriction. You're close. There's a part in there that I don't quite love. It's not a domain restriction. Destiny, what are you seeing?
Is it a y?
There's a restriction on the y? What's the restriction that you see on the y?
Because it's square root of y, and so it's no negative square root.
Right. If you look at the original differential equation, what we see is that we've got square root of y. So what's the not domain restriction, but range restriction? What's the restriction on the range? What has to be true about the y values here?
X has to be positive.
Greater than 2.
Okay, don't tell me about x. I'm not interested in x.
It has to be positive.
Greater than
Y has to be positive. It could be 0 though. Right? We can have 0 for the y's. That's okay. Any domain restrictions while we're here? Any
Yes.
domain restrictions, Jackie? Domain restriction? What's your domain restriction?
X greater than 2.
X greater than 2? I disagree with x greater than 2.
X greater than or equal to 2. No, that's
What can't we have in the domain?
2.
2. So x can't be equal to 2. So when you talk about your domain, you either are going to pick values of x that are less than 2 or values of x that are greater than 2. But you can't pick both. Okay? Now look at our solution curves here. The red one is strictly going to be x is greater than 2. The green one is going to be strictly x is less than 2. Because what happens at x equals 2, what you actually have, they're hard to see, you have vertical tangent lines. And the reason you have vertical tangent lines is at x equals 2, you would be dividing by 0 and the slope is undefined. My sketch is a little bit bad. It looks like I crossed my vertical tangent line. I shouldn't have, because we know that our solutions always have to be, hold on, continuous functions, and we need the domain. Because of your vertical tangent lines at x equals 2, your graph stays completely to the left of 2 or completely to the right. Paul, what was your question?
So they're gonna be like 3 responses where we have to sketch these?
Possibly, yes.
And if we like wouldn't cross the tangent line, we would say,
Then you would lose some points because you need to know, because of your domain restriction, x can't be equal to 2, so I can't cross this line. I'm going to get close to it, or I'm going to start just after it, but I can't cross it. All the friends are okay? Slope fields should be a very comfortable, friendly thing for you. You're just doing some sketching. Now what I want to do is see what you can do with part C. Using separation of variables, I actually want you to solve this differential equation, subject to the initial condition y of 1 equals 4. Once you're finished, generate the graph of the function. Show me what you can do. You need a ruler. Okay, rulers are my selection. No, I'm not talking about that.
You could have marked that.
I have a different pet name for him. Oh, go ahead. Y dx equals square root of y over 2 minus x. How are you going to solve that differential equation? A lot of what I'm seeing there. There's some really good stuff there.
That's what
You
I'm
want to
wondering.
do square root of y, those are negative.
But I mean, if you plug it in, right? dy plus 2. So it must be 2. If you plug it in.
Oh, strike out in so many
So
places.
x equals 1 and a equals 4. Assumption is 0, right?
So as expected, a lot of folks are multiplying both sides by dx. So we get dy equals square root of y over 2 minus x dx. Great. Haven't separated the variables yet. So what's next?
Divide by
Divide by square root of y. Everyone seems to be okay with that. So now you've got dy over the square root of y equals 1 over 2 minus x dx. Have we separated the variables? Flo, are you good if we've separated the variables? Okay. So now what? You're going to integrate both sides. You're going to integrate. You're going to integrate. Getting here gets you the first point. Now, I'm seeing mistakes happening on both sides of the integration here. On the left, folks are choosing to rewrite this as 1 over y to the half. That's good. Right? Square root of y is y to the half. I think a lot of folks are like, oh, power rule. I need power rule here. But this isn't ready to be integrated using the power rule. Right? I'm seeing a lot of folks said, oh, add 1 to the power, divide by the new power. But you're in the denominator, so first of all, you've got to rewrite this as y to the negative 1/2 dy. Now add 1 to the power, then divide by the new power. And if that goes well, what do we get?
2y to the power of 1/2.
2y to the power of 1/2. Now you've picked up your first point. Okay? On the right-hand side, the mistake that I keep seeing is a lot of folks are seeing the 1 over 2 minus x, and they're saying that this is the natural log of the absolute value of 2 minus x plus Charlie. Having the plus c, that's good news. It's not going to integrate as the natural log. And if you're not sure why, I think a lot of folks are seeing this like 1 over. Right? You're like, oh, it's 1 over stuff. Take the derivative. What happens with the derivative process here? Derivative of natural log of stuff would be 1 over the stuff times the derivative of the stuff. And the derivative of the stuff is negative 1. You're getting not 1 over 2 minus x, but you're getting the negative of this. So the way you adjust for it, it's going to be negative the natural log of the absolute value of 2 minus x. If you're not loving that, your other option, try substitution. Let u equal 2 minus x. And if u is 2 minus x, then the derivative is negative 1 dx, and you'll get that negative to show up. So where everybody should be now is that you've got 2 times y to the half is negative natural log, absolute value of 2 minus x plus c. Finish it off. Solve it for y. Use that initial condition. Make sure you give me the domain. So divided by 2, that's it. Oh wait, so you found the initial conditions? C is 4, okay, I think that's right. Okay. Taking the square root is not the right way to go. Oh, you already have 1 to the half, which means square root. You need to do the other half. I need to square both sides.
Yeah, let me stop this.
My initial condition, x equals 1 when y is equal to 4. 2 times 4 to the half equals the negative natural log, absolute value, 2 minus 1 plus c. 4 to the half is 2 times 2 we get 4. 2 minus 1 is 1, natural log of 1 is 0. C is equal to 4. 2 times y to the half is equal to negative natural log, absolute value of 2 minus x plus 4. Walking around, it looked like just about everybody was able to find the initial condition, or use the initial condition to find c. To finish this off, you're going to divide both sides by 2. I love it. And the last thing, square root both sides or square both sides? Right, this y to the 1/2 already means square root. To solve for y, you're going to square both sides. So y is negative natural log, absolute value 2 minus x plus 4, divided by 2, the whole thing squared. Are we worried about this being a function? I'm not too worried. I don't see a plus minus weirdness showing up. I don't have any of that business going on. So we've solved for y. We've got the initial condition. We seem to have a continuous function. There's only one thing left. Give me the domain. What's the domain for this one? All real numbers. Remember, we can't use x equals 2. So you're either picking values to the left of 2 or you're picking values to the right of 2. Which one?
Other.
When in doubt, the way that you choose is you go to the initial condition. Where's the initial condition? The initial condition says y of 1 is equal to 4. I'm on this side. So your domain is going to be x is less than 2. This is your full points, all the way correct answer. The slope field helps you visualize what the solution looks like. Separable differential equations, if you can separate it, will tell you what the final equation is. And that's where we are. You guys have a couple minutes left before the bell rings. I would recommend using this time to start making the corrections to the quiz. For anybody who's interested, we're going to talk about part A. We've got 2 minutes. We can talk about part A of the quiz, as well as a little step that everybody gets themselves tripped up on part B. And Jesus, if you could turn off the camera, I don't want my salute.